for coming. Thanks to the organizers for putting on the nice conference. Yeah, so I'm going to talk about some work that I've been doing in my thesis and sort of beyond. And yeah, I'm going to sort of, as a palette cleanser, I'm going to start with a real analytic family of modular forms instead of a p-adic family. So to start, I want to discuss sort of Gross-Naggier's paper on singular moduli, which is kind of one of the inspirations behind this work. And so the starting observation is that if you look at the Klein J invariant evaluated at two different CM points, so here they both have class number 1, then you get some big number usually with a very strange factorization. So you can see that all the prime factors here are very small. Right, but I think maybe some accidentally got chopped off. There should be some bigger prime factors as well. But these are very unusually factored, and this was noted by Berwick in the 1920s, and later in later in the 80s, Gross and Naggir asked more generally, if we take two CM points, look at the difference, we get some kind of algebraic number by CM theory, and if we look at the norm of that down to Q, that's going to give an integer. And what can we say about the fact that they made lots and lots of computations, famously on a small calculator, and they actually gave an explicit formula for the factorization of the differences of singular moduli. So they gave two proofs of this. One of them was an algebraic proof, which used kind of CM theory, and the other one was purely analytic. So I kind of wanted to describe the analytic proof because that's the one that's that we're going to generalize or sort of adapt to different setting. So what's going on here? So first of all, you have two imaginary quadratic fields coming from tau 1 and tau 2. And the composite is a biquadratic field, which contains a real quadratic field F. And this biquadratic field determines a genus character chi of F. And what they did was they considered a certain Hilbert-Eisenstein series. This is the real analytic family of Hilbert modular forms that I alluded to a moment ago. So this is an analytic thing. It's not for various values of S. It's not going to be holomorphic. But famously, when you plug in S equals 0, you get 0. And I write that this is sort of due to Hecke, but actually Hecke thought it was non-zero, and he was very happy because he constructed sort of a trivial level parallel weight 1 modular form. It was only realized later by Schoenberg, I think, that this is actually 0. So one thing I do want to point out is that you can write this down really explicitly. So the constant term is some L value, and the Fourier coefficients are some sort of generalized devices. And this is kind of what powers this analytic proof of Gross and Naggier's explicit formula. So what are we going to do? We're going to start out with this Eisenstein series, which we know vanishes at S equals 0. And then we're going to take the diagonal restriction to get a classical modular form. So taking derivative of this thing at S equals 0 is going to give you something that might be interesting. So this is going to be, sort of for formal reasons, this is going to be an analytic modular form of level SL2Z. So now we have a classical modular form of weight 2, but it lives in some sort of analytic space. It's not a holomorphic modular form. But we can always project onto the subspace of holomorphic modular forms. And this is what this Proj-Hall thing is. And this is 0. And why is this 0? Well, it's 0 because it lives in a space which only contains 0. So weight 2 modular forms of full level SL2Z. Okay, so they had something that at 0 was 0. They took the derivative of this thing, and they got 0 again. So why is this useful? Well, I told you earlier that the Fourier coefficients were very explicit, and in a similar way, they very carefully compute the explicit Fourier coefficients of this this modular form, which happens to be 0. And so what they get is that the first coefficient, so this is not a constant term, but the A1 coefficient, starts out being a logarithm of this norm of differences of singular moduli that they wanted to study. And then they get a sum, a finite sum, so I haven't written it here, but a finite sum of certain numbers times the logarithms of Q. And this is still 0 because it's the coefficient of the 0 modular form. So what they do then is they rearrange this sum, and then they exponentiate. And what they end up getting is a product of a primes Q and these sum factors that I haven't bothered writing down explicitly. And I've written here on the right that this is the height pairing of Heegner points on this tau1 and tau2 on x1. And this sort of sparked a very general program by Gross and Sageer, and later expanded by Gross, Conan, and Sageer, where they compute heights of Heegner points on more general modular curves. And that's the basis for the Gross-Sageer formula and so on. I just want to mention this because it's going to appear later today in Leonard's talk, and yeah, I think his talk is going to tie very much in with what I'm talking about now. So I just want to point out another thing which is relevant for my work, is that Hutchinson made a bunch of conjectures for so-called non-fundamental CM points, tau1 and tau2. So Gross and Sageer's result only holds when tau1 and tau2 sort of generate the ring of integers in the relevant imaginary quadratic field. And up until now, there's been no sort of progress on these conjectures for non-fundamental CM points. So like when you get a non-maximal order in your imaginary quadratic field. But a proof has been announced by Yoshinori Mizuno, who's in Nagoya University in Japan. And hopefully this should appear at some point shortly. Yeah, so the goal for the next few minutes is to describe sort of real quadratic and p-adic analogs of this. So do this sort of derivative argument, this holomorphic projection in sort of in a p-adic setting, where we replace the CM points with real quadratic fields. So first I want to sort of describe a reinterpretation of Gross and Sageer's result due to Howard and Yang. So this is a really nice paper called Singular Moduli Refined, which I think appeared in 2012. And I've sort of abstracted out the diagram of fields from before here. So we have two imaginary quadratic fields, F1 and F2, and a real quadratic field F, which is where the Hilbert modular form lives. So the goal of their paper was to sort of contextualize Gross and Sageer's results in terms of the Kudla program. And this is sort of, yeah, this is, I think this in itself is not new, but they realized that the Eisenstein series that they considered was a so-called incoherent Eisenstein series. And this is sort of a real analytic family of Eisenstein series that vanishes because of the functional equation. This is something that sort of is one of the main tools in the Kudla program. Yeah, just written again. This E chi, Hilbert Eisenstein series, is actually a theta lift from a certain orthogonal group to SL2OI. And they use that to sort of interpret not just the coefficients of the derivative of the diagonal restriction, but the original Hilbert itself. And in particular, instead of these CM points in the classical description, we're going to think of F1 and F2 as defining embeddings into the quaternion algebra that's 2x2 matrices of a cube. And this is kind of a more powerful framework that we can generalize in terms of real quadratic fields. So yeah, I'll just repeat that here. First of all, there is no CM theory, which means that there is no algebraic geometry, which we don't have in the real quadratic setting. And sort of on a purely formal level, we can replace this diagram with F1, F2 being real quadratic fields. F1, F2 is a sort of totally real biquadratic field, and F is still a quadratic field. Okay. And before I state the main results, I have to do sort of make a little excursion into the description of real quadratic geodesics. This is kind of setting up what happens when you try to replace CM points with these real quadratic things. So I'm going to fix for later convenience, I'm going to fix B in indefinite quaternion algebra, but for convenience, you can just think of this as the 2x2 matrix algebra over Q for now. And I'm going to fix an Eichler order OB. So this is not unique, so it's not the ring of integers. But yeah, you might think of things which are sort of upper triangular mod P inside the matrix algebra. So now suppose that there exists an embedding of a real quadratic order O into this Eichler order. So this doesn't always exist. This has to do with sort of local conditions. Assume that one exists. Then we can look at the image of the units of F tensor R inside the symmetric space of the units of this quaternion algebra. And what does this look like? Well, if you do the computation, you simply get a geodesic inside the upper half plane. And it's characterized by the fact that its endpoints are sort of real quadratic points, which corresponds to this order for some tau in the order. Okay. And we can also mod out by the action of the units to get, well, if you do it for the quaternion algebra, you get the Shimura curve. And if you do it for the order, you get a closed geodesic. So you can think of this as taking a little line segment in here, corresponding to moving a point along by the action of a fundamental unit. And then you take this little line segment and you map it into the fundamental domain of the Shimura curve. And so if B is not a matrix algebra, if it's a sort of proper indefinite quaternion algebra, then this is a compact curve. And so it's simple, very simpler to understand. And another thing I want to use is that once you have an optimal embedding, you can look at sort of inequivalent embeddings. I'm not going to explain what optimal means, but you can ask me later if you really want to know. So if you have one such embedding, you can look at things which are not conjugate. So I can conjugate by a norm 1 unit and get a new embedding. But I can also look at sort of inequivalent, like non-conjugate embeddings. And it turns out that these are in bijection with a narrow class group of the order that I started with. And so I'm going to fix the character psi of the class group. So this is the so-called ring class character. And I'm going to define sort of a formal linear combination of geodesics inside the Shimura curve. Okay, so now let me state or try and get to the first result. So this is kind of a degenerate case. So I'm going to start out with, instead of taking two real quadratic fields, like I told you in the beginning, I'm just going to say let one of the real quadratic fields be q plus q. So this is some kind of like flake real quadratic field. And if you sort of if you take a real quadratic field f, then the sort of final intermediate field is going to be a real quadratic field as well. Okay, and what I need to have an embedding alpha like before is the condition that P is split in F. And then it turns out that the image of the units is going to land inside gamma naught P. On the other hand, you can sort of run the calculation and see what you get when you embed kind of like the real points of q plus q, or the units in q plus q, into the upper half plane. And what you end up getting is line from 0 to infinity. And this defines a homology class on the, I guess, like in relative homology of the closed modular curve x naught of P. And as before, I'm going to take psi a character, but I'm going to assume that it's totally odd, and that's kind of necessary for things to be non-zero in the theorem. I'm also going to define a certain Hilbert Eisenstein series. So this is kind of the normal. You start out with the normal Hilbert Eisenstein series, so parallel weight 1. But then you P stabilize it, and that's what I mean by this P. So you kind of, then you choose the nice P stabilization, I guess. And for sort of technical reasons, I'm going to take the level structure for this guy to be SL2 of the order intersected with gamma naught. So that's kind of where so this is kind of an unusual Eisenstein series, unusual in the sense that it hadn't been written down before, but it turns out to be the right one for our applications. Of course, if psi is unramified, so if O is the maximal order, this is the Eisenstein series that we know and love. Okay, and then a theorem which was proved by Damm Johnsen and Wonk a little while ago in the fundamental case in which I extended to these non-maximal orders is that with our setup, you can describe the intersections on the Shimura curve. Sorry. Between the image of q plus q, so this geodesic connecting 0 and infinity, and the nth Hecke translates, I'm translating by the Hecke correspondences, of this linear combination of real quadratic geodesics delta psi. So the intersection number, the topological intersection number, is exactly the diagonal restriction of this Hilbert modular form. And of course, we can read off the constant term from the right-hand side, and it turns out to be an L value.
Sorry, I'm a little bit lost. Like the Shimura curve, it doesn't have cusps, right?
Sorry, now we're in the case M2Q.
Oh, okay.
So it does have cusps.
It's Eisenstein series is just attached to 1 plus phi,
Yes.
1 plus c, I mean, but. So
Yeah, but it's not gamma naught of n double structure. It's a genuinely different thing.
But it is what it is. I'm sorry, like.
I mean, it looks
Attached to 1 plus c, you have only one Eisenstein series. What do you mean?
well. I can define my Eisenstein series, however. But it's not the usual, and it's not the usual one to think about. Like I've written down for your expansion of something genuinely different, and I can write it down for you later if you want. But yeah,
So it's not the usual attached to 1 plus c.
No, it's not the usual. But sort of, yeah, the constant term is sort of an more or less this L value.
Because usually to have Eisenstein series, you need cusps, right? Here you
Yeah.
don't have cusps, so that's why it's unusual.
No, you do have cusps. You're in the empty
Q.
Q.
Okay,
Yeah.
okay, because you keep saying.
Sorry. That's yeah. So you can't have an embedding of Q plus Q into an indefinite Q-standard algebra. It's not Q plus empty Q.
If I could ask a question, when you write LP here, is that a genuinely p-adic L value?
No, it's a classical L value. Like
Okay,
just
so
for
the P just means you've modified the Euler factors.
okay. But now I want to talk about the sort of incoherent case, which is kind of the one that should mimic the Gross-Segger case more. So first observation is that when P is a nut, for kind of stupid reasons, this Eisenstein series vanishes. And there are also the condition, which I told you was necessary for the embedding of this order into gamma naught of P, is no longer satisfied. So there are no optimal embeddings. But surprisingly, it turns out that we can still say something that's quite interesting. So again, with psi a totally L ring class character, if we run the Gross-Segger argument in a p-adic setting, so we're going to start out with a p-adic Eisenstein family, which goes through the same Eisenstein series from before. We take the derivative in big space and evaluate at k equals 1. Then this is still an overconvergent modular form. I'm going to take the diagonal restriction like before. And this is some overconvergent modular form that you can sort of write down quite explicitly. I'm going to take the ordinary projection to get a modular form of level gamma naught of P and weight 2. And it turns out that this has a very explicit Fourier expansion in terms of these rigid analytic co-cycles defined by Darmo and Bonk, which I won't have time to go into. And the constant term is the p-adic logarithm of a gross dark unit. Another sort of point of view is that these JW evaluated at the delta psi can be thought of as some kind of p-adic intersection number. So it's some kind of Darmo style intersection number on HP cross H. And this construction is completely explicit, and so you can use it to give an algorithm for computing values of this JW and the gross dark unit. And it's, yeah. So I should say again, for unramified character, this was proven by Darmo, Pozzi, and Wonk, and I extend it in my thesis to unramified, to ring class characters, ramified ring class characters. Yeah, and this method, this sort of p-adic method of taking a p-adic derivative of a family, which vanishes at a certain point, and then taking the ordinary projection, is also something that features in Mike Doss's work and in the work that Lennart will talk about later today. And it seems to be very powerful and flexible. All right. So in the last 5-10 minutes or so, I want to talk about a real quadratic analog. So now we're in the sort of non-degenerate setting, where we work on compact Chimera curves. So now I'm going to explicitly exclude the case M2Q because that was covered in the previous slide. So I'm going to fix B in indefinite quaternion algebra, and I'm going to fix a pair of optimal embeddings alpha 1, alpha 2 of two different, possibly different real quadratic fields. So then again, I can consider these intersection numbers that appeared in the first theorem I mentioned, and these were computed by James Rickards very sort of extensively in his thesis. And the picture you get by mapping into the upper half plane is kind of two geodesics that intersect in a certain way. And the theorem that I want to explain is the following. So if you start out with this Eichler order as before and two optimal embeddings, then just like before, you can find some Hilbert modular form whose diagonal restriction is exactly the generating series of these intersection numbers on the Schmirer curve. Right, and the work in progress means that I haven't yet figured out exactly what the level is, which might be apparent from the proof, which I'll sketch. But yeah, this is the theory. Are there any questions about this?
I have just a question about when you refer to the procedure. It's used there is no like level 2, level 1 weight 2 forms, right?
Yeah.
So here, what replaces this?
Right. So it's kind of used up here. So the vanishing of this the thing uses the fact that there are no.
That's a replacement for.
That's the replacement. Yeah. So the point is that when P is inert, sort of P stabilization gives diagonal restriction, and so when you diagonally restrict, you can sort of you end up getting 0, and then when you P stabilize, you still get 0, and so this thing is still 0, and that doesn't. Yeah.
Oh, so it's still SL plus D kind of argument.
Well, no, it's kind of in a. I'm not explaining this in a very good way. So this is kind of, I guess, a bit orthogonal. So what Grossenzagier do is that they always end up on the like full level modular cap, and then they get something which is necessarily 0. What we do is we end up with something known to gamma naught of P, and so that's not automatically 0. But I guess it's still interesting is the point. So we can't necessarily prove the same kinds of formulas, but when I'm referring to the Grossenzagier method, I really mean this considering something that vanishes, taking the derivative, and then the ordinary projection. Does that make sense?
Yeah. So, but it's not 0 at the end.
Yeah. No, it's non-zero, and that's, I guess, it's non-zero in an interesting way.
Right.
All right. So yeah. So now I want to explain something, unless there are other questions, I want to explain something about the proof of this, because I think it's quite nice. So this is something I should say, I forgot to write it in my slides, but this is based on work of Romain Branchereau, who gave a new proof of the first theorem that I showed, using sort of Kudla program techniques. And this is kind of similar. So we're going to start out with considering B as a quadratic space with a norm form signature 2, 2. And so the idea is that we're going to work with the orthogonal group of this thing. And the two real quadratic fields that I have are going to give me a product of tori. So I'm gonna take the product and require that the norms are equal, and this embeds into SO of B. So very explicitly, if I have embedding alpha 1 and alpha 2, then I can act by alpha 1 in the first component and alpha 2 in the second component. Sorry, embed via alpha 1 and alpha 2 in the second component, or alpha 2 bar. All right. And if you think about this, if you stare at this for a bit, you realize that the symmetric space of SOB is more or less the upper half plane across the upper half plane. And now the Kudla-Milson, so Kudla-Milson constructed this theta lift, which actually gives you a differential 2 form on the upper half plane, and it has this property that when you integrate it against, well, anything, here in particular C1 cross C2, it will give you. I'm missing a sum over n here. Yes, sorry about that. Yeah. So the moral of the story is sort of that the nth Fourier coefficient of the Kudla-Milson theta lift is Poincare dual to the nth Hecke correspondence, and this is kind of a theta lift from SL2 up to SOB. Okay.
So Cn is not C1 when n equals 1, right?
No, it's not. I'm sorry. That's the nth Hecke correspondence. So this is something that you can think of as living inside H cross H, or you can think of it as living inside the product of America itself. And so yeah. So there should be a sum over all n, and the n is the Hecke correspondence. And then for just topological reasons, when you intersect the Hecke correspondence with the product of these two geodesics, what you get is exactly the intersection number that we considered before. And now we're going to do sort of a change of model argument. So Howard Yang used in their work that there is so they did it in a different setting with definite quaternion algebras, but their argument works in this setting as well, and it says that we can find an isometry between quadratic spaces of B with a norm form and F1, F2 with this strange quadratic form. So this is a 4-dimensional space over Q, and it has this thing which you can check is a quadratic form. And this is what we're going to use to sort of cook up our Hilbert modular form. So we have this seesaw diagram on the right, which is something that's used often in the Kudla program. So we can compare upstairs here. We can compare the orthogonal groups corresponding to the orthogonal spaces that we considered, and it turns out that you can map this T from before, this thing which morally gives you the product of the geodesics, onto the restriction of scalars from F of SO viewed as a quadratic space. Sorry, of SO F1, F2 viewed as a quadratic space over F. And then the main idea of the argument is to do a theta lift from sort of bottom left to top right. Is going to give you the Hilbert theta series from before. And on the other hand, the theta lift from SL2 to SO F1, F2 is what gives you, and then sort of integrating over the embedded thing on the bottom is what gives you the intersection numbers. Right. That was a bit quick, but I'm running out of time, so I'm gonna. You can ask me questions about it later if you have them. And of course, the hope is, or the dream is, to upgrade this to something that you can do in a p-adic setting. But for various reasons, that seems quite difficult. But it's sort of ongoing work by Damm Johnsen, and it should morally give you a p-adic height pairing of real quadratic geodesics, whatever that means. Right. I think I'm going to end here, and thank you for the attention.